Hi everyone, my name is Will Gibbs. Thank you for coming to my talk about Operation Mango. And before we get started, I just wanted to say that problems like these are hard and difficult problems require scalable solutions. So as you can see, our author list also scaled to the USENIX security approved 15 authors. So firmware lives in devices that you all use every single day, like routers, NASs, cameras. All of these devices run on firmware. But in 2024 alone, more than 300 CVEs with CVSS scores greater than 8 were published in just 4 major vendors that I looked at. However, auditing these devices is not straightforward. Source code is not generally available, and physical devices are expensive and difficult to test at scale. So binary analysis is necessary to find these vulnerabilities faster and more efficiently. But first, we need to understand how these devices work. Firmware can be separated into 2 common categories. First, you have blob-based firmware, which is just that, a cohesive blob of disparate utilities and binaries stuck together, all into one big guy. And then you have Linux-based firmware. These firmware run on tiny Linux distributions like Alpine and implement their functionality in individual binaries. And we're gonna focus on Linux-based firmware. You can't analyze these firmware binaries independently. You need to have knowledge of how data flows between them in these multi-binary systems. Otherwise, you're going to end up with a lot of false positives. So one popular method for these binaries and their multi-binary interaction is NVRAM, the non-volatile random access memory. This really just acts like a key value store for the programs in operation. You can see here we have HTTPD storing a value into memory. And then you have a separate binary that's using an NVRAM get to retrieve that value from memory. It's really fairly simple. However, your generic static analysis can't handle this type of multi-binary interaction. And so to handle this, prior work Caronte used an under-constrained symbolic-based taint analysis to find constraints on inputs and propagate them across this NVRAM boundary. But any of you who have actually used symbolic execution know that it's really not scalable. It's actually so unscalable that you can't process input across all of these binaries at once, right? So what Caronte did to solve this issue is they scoped it down. They created this concept called border binaries, in which only external input that was being fed into this firmware, only those binaries that were processing it and parsing it were actually considered. A follow-up work, SaTC, narrowed this scope even further down. So they decided that user input flowing from front-end interactions, such as UI panels, management panels, config administration, goes from a front-end web service to a web server, such as HTTPD, until ultimately it hits the back-end utility. Now, this actually allowed them to not only speed up analysis, but find even more bugs. But we think that there's even more bugs hiding in these binaries that nobody's looking at. And so with a better static analysis, you could, in fact, analyze all of the binaries. So we created Operation Mango, an improved static analysis for Linux-based firmware with 4 key things in mind. And a quick note that this tool works on all architectures supported by Anger. However, all the examples I'm going to show you are in source code for ease of understanding. So we have MANGODFA is our static analysis value dependency engine that we created and implemented in Anger, the binary analysis platform, as its reaching definition analysis module. So let's track the value of name here in our code example as it flows through until it ultimately hits our sink of system. This is how our value dependency analysis actually works. It's relatively simple. First, you can see the user input is received through fgets here, which then flows into another function who's called, which ultimately their argument flows into snSprintf, which is transformed into the variable of command. And then we hit our sync system, right? Relatively easy. You're just tracking the value as it depends on each succeeding value. And so the values that we are tracking here are what we call rich expressions. These allow us to track or to encapsulate the history of the value at any location. So going back to our snippet here, let's follow name again. You can see we start out at fgets, but then after going through fgets, we retain the history of being called by fgets. You can see that on the right-hand side here. And then we follow through sub 401080, and this gets continued to be included in our sprintf. However, you can see that the command value that gets transformed, we actually include the history of fgets in that value. You have the concatenation of the literal string and our history as well. And so when that ultimately flows into our sync of system, we are able to track very easily of, oh, this is our input, this is where we came from, this is our history, right? But let's back up for just one moment here, and I'll modify our format string to be unexploitable, right? A %d. Now, even though that we have user input, unidentified input flowing into a potential problem area here, we know that it's not exploitable. We can actually resolve with our function handlers that this sprintf doesn't matter to anybody. Because no matter what that value is, once you hit that %d, you're now no longer able to produce a command injection here. And so our next two improvements were created with the intuition of how human reverse engineers actually reverse binaries. We have assumed non-impact, which helps determine which functions are important to analyze and which are not during our taint analysis. So let's start again, but let's pay attention to these two extra lines that I added. We have start background task and validate name. So as a reverse engineer, you see fgets, right? You see, oh, this function probably important. It's where input's coming from. Then we move on to our next function, start background task. This function doesn't actually have anything to do with our value of name that we care about, so we decide this isn't important. Let's not analyze it. And we continue through how we had normally until we hit validate name, right? And then you would see this and you say, hey, our name value is flowing into this. There's a dependency on it. Maybe this is something interesting. We have to look deeper at this. So let's look deeper at it, right? And that's how that's the intuition behind assume non-impact works, how reverse engineers like you and me would actually analyze this binary. And then finally, we have our sync to source coarse grain analysis, which allows us to scope our overall analysis down, removing any extraneous input. And again, a reverse engineer would start at the sync probably, right? You start where you think the program might be vulnerable and work backwards to try and see, hey, is there any place around here that might not be vulnerable, might not make this possibly injectable? So we'll start again where system uses CMD. And then we actually work our way back up through sprintf, through validate name, ultimately to the call site of sub 401080, where we can work back one more time to fgets, and we say, hey, we've reached our input, right? We've found all possible sources of input to this program for this specific sync. So let's just stop here. We don't need to look any further. We don't need to back up anymore. And this allows us to eliminate any possible extraneous functions or scoping required. But does this really work? So let's take a look at our last two optimizations and how they improved our overall analysis. We did an ablation study on the Netgear R67 router, for those of you interested. And this is the average execution time per binary. So with no modifications, with neither of our optimizations applied, it takes us more than 1,500 seconds per binary to actually analyze it. But then once we apply both, we lower that down to less than 300 seconds per binary, a more than 5 times increase in actual analysis speed. And then does this actually find bugs, right? So with this increase in speed also comes an increase in true positives. After applying both of our analyses, we find 8 more true positives than through our initial method. And we can further see that after applying our source to sync, or our sync to source analysis on top of the assumed non-impact, even though we stay the same amount of true positives, we actually have less false positives because we're reducing our scope, we're reducing the context that we need to actually analyze, so we have less false positives overall. Operation Mango was evaluated on the same dataset as prior work used, SaTC, on the Coronte dataset of 49 firmware. We generated 2,300 alerts over all of the tested firmware. We randomly sampled and analyzed 100 command injections, resulting in 57 true positives, 230 buffer overflows in 109 true positives, with about a 47% true positive rate. So overall, this gives us a 52% true positive rate, or a 1 in 2 alert being vulnerabilities. Now let's compare directly against SaTC on this same data set of 49 firmware. We completed all of these experiments on a single core. You can see that we analyzed almost 30 times as many binaries. We generated 16 times more alerts. And we found vulnerabilities in 3 times as many programs. This is with a 9% overall increase in time spent analyzing, but a 22 times decrease in average analysis time spent per binary. So just to recap, we found bugs in 3 times more binaries at 22 times the speed per binary. We manually verified 166 exploitable vulnerabilities. Operation Mango is open source and available. It will continue to be maintained on the Anger platform as well. You can find our project, Operation Mango, here on the CEFCOM GitHub, and thank you all for coming to my talk.